I guess that after finishing the quiz, you might think that there are so many permutations for 12 terms. How could we list all these permutations? Let's think about it carefully. How should we generate all the permutations? For this problem, could we look at the simple example and first? For example, when there are only one element. So there is only one element, there is one permutation. What if there are two elements? For example, the two elements are 1, 2. Now we found that for 2 relative to 1, it might be before 1 or it's after 1. Now with this idea, let's think that could we generate permutation of 3 with permutation of 2? For example, we already have 1, 2 and 2, 1. Now we also have 3. For the position of 3, it could be moved from right to left 1 by 1 in a permutation of 2. So now I have a series of permutation of 3. Similarly, for any permutation of 2, for example 2, 1, we could move 3 from left to right. We could discover that by moving a new element in a shorter permutation, we could get a longer permutation. For those who studied computer science, we should know that this is the idea of recursion. It could generate permutation of n with permutations of n minus 1. But we all know that there are some problems with recursion. The idea and the implementation are quite simple, but it's pretty complex. And in reality, it would use a lot of memories. So we hope to have some more direct method to generate them. Is there any familiar permuting method? Look at what's in my hand. It's an English dictionary. There are permuting methods in dictionaries. We call this method lexicographic order. So dictionary gives us some implications. We could sort them by some order. For example, let's assume that there are 3 letters. A, B, C is the smallest permutation. What's after? Let's add only a bit. We discover that we need to try to keep high-order digits and try to increase low-order digits only a bit. After ABC, if A is kept unmoved, how should we increase BC? We only need to exchange B and C to get the next permutation, which is ACB. So what's the next of ACB? Let's think carefully. If A is kept unmoved, CB couldn't be increased anymore. So how should we increase it a little bit now? We need to increase A by changing it with B. Then in order to keep the word only a bit larger, the suffix after B should be as smaller as possible. The smallest permutation of A and C is AC. So this is the string we want. We found that we could sort the permutation with lexicographic order. We just introduced that we need to divide a string into prefix and suffix. In the process of increasing permutation in lexicographic order, we need to try to keep prefix the same and increase suffix one step at a time. This is the idea of lexicographic generating algorithm. With this idea, it's not hard to list all the 3 factorial permutation of A, B, C in order. In order to make it clear, we use numbers instead of letters to analyze it. For example, for 3-digit number 1, 2, 3, among all the 6 permutations of 1, 2, 3, let's analyze how to construct it by lexicographic order. The key idea of lexicographic order is to keep the prefix as long as possible and to increase the suffix slowly. Let's analyze. How should we generate the permutation of 1, 2, 3? At first, we will try to keep the suffix as small as possible. We need to analyze whether it's the shortest suffix or not from right to the left. So in what situation would the suffix be the largest? Let's analyze carefully. For example, increase 1 to 3 one step by a time until the last sequence. We find that the last permutation is actually 3 to 1. So if we scan from right to the left, we find that the numbers are sorted ascending from right to the left. So the suffix couldn't be increased anymore. With this idea, we think that when could we make change to increase it a little bit? If we scan from right to left, we discover that it's no longer ascending, but rather descending. This means that we could increase it a little bit here by exchanging. So our idea is to scan from the right to the left and first. When finding the first descending position, for example, here 1, 2, 3, we scan from right to the left, we discover that 2 is the first descending position. So what should we do then? We could increase 2 a little bit. This means that we could exchange 2 and a larger number in the right. Here we exchange 2 and 3 to get a new permutation, which is 1, 3, 2. Then let's continue. Scan 1, 3, 2 from right to the left. We discover that we could make a change and the position of 1. What should we exchange with 1? 3 or 2? Both of them are larger than 1, but we should choose the smaller one to exchange. For example here, if I exchange 1 and 3, we would change the prefix too much. So we choose the smallest number among those who are larger than 1. So we would exchange 1 and 2 in 1, 3, 2 to get 2, 3, 1. Is 2, 3, 1 only a little bit larger than 1, 3, 2? Actually, the 3, 1, the suffix of 2, 3, 1 is not the smallest suffix. We only need to exchange 1 and 3 to get a smaller 1, 2, 1, 3. So we would find that the next permutation of 1, 3, 2 in lithographic order should be 2, 1, 3. So forth. With this idea, we could generate all permutations with lithographic order. What's the key? At first, we need to guarantee that we are scanning from right to the left and find the first descending position. This number will be exchanged with the number who is the smallest among those who are larger than it in the suffix. Finally, guarantee that the suffix is smallest suffix. So we could permute in lithographic order. Then let's take a string as an example to see how to generate the next permutation in lithographic order. We use 83964751 as an example. How does lithographic order work? To find the next permutation, we need to scan from right to left to find the first descending position. Right to left, 2, 1, 5, 7. When right on 4, it turns into descending from ascending. So here we would discover that 4 could be exchanged with another digit in the right to the increased value. So who should be exchanged with 4? There are 1, 2, 5, 7 in the right of 4. Of course, we need something larger than 4, and we couldn't exchange with something much larger. So we'd have to find the smallest one among those larger than 4 in the suffix. Here, 5 is larger than 4, and it's the smallest one among them. So we choose 5 between 7 and 5. After exchanging 4 and 5, we get a new permutation, which is this one. Now, we need to guarantee the suffix to be the smallest. 7421 is ascending from right to left, so it's the largest suffix. So if we want to make it smallest, we only need to flip it over and make it 1247, which is ascending, and it's the smallest one. So we could perform this 3-step and get that the next permutation of this one is that one. We just calculate that the next permutation of this string is 839651247 in lesser graphic order. Comparing these two numbers, we could discover that although they are adjacent, there's a huge difference. So we could think that actually we want to generate a new permutation with only a micro difference. Next, we will introduce another method.